Imagine two ice skaters at rest who push off each other. One glides left, the other glides right. No engines, no ropes, no mystery force from outside, yet motion appears. What stays fixed is not velocity or energy, but total momentum. Momentum is defined as mass times velocity, P equals mv. It is a vector, so direction matters. A heavy object moving slowly can have the same momentum as a light object moving fast, but opposite directions count as negative. Momentum conservation is never about a single object. It applies to a system, meaning the collection of objects you choose to analyze. The rule is simple and precise. The total momentum of an isolated system stays constant. Isolated means the net external force on the system is zero. Formally, total momentum P equals the sum of all individual momenta. The fundamental law is dP over dt equals the net external force. If that force is zero, then dP over dt is zero, which means P does not change. Initial total momentum equals final total momentum. Why does this work? Newton's laws give the answer. Each object in the system obeys Newton's second law. The rate of change of its momentum equals the net force on it. Forces come in two types: external forces from outside the system and internal forces between objects inside the system. When you add up the momentum changes of all objects, every internal force appears twice, once as an action and once as an equal and opposite reaction. Those cancel exactly. Internal forces can move momentum around inside the system, but they cannot change the total. Only external forces can. This is why collisions are so clean to analyze. During a short collision, the forces between the objects are enormous, but external forces like friction or gravity act for such a short time that their impulse is negligible. With essentially zero external impulse, momentum is conserved during the collision, even if energy is not. In one dimension, a two-object collision obeys m1u1 plus m2u2 equals m1v1 plus m2v2. This holds for elastic collisions, inelastic collisions, and perfectly inelastic collisions where objects stick together. Kinetic energy may decrease, but momentum does not. Momentum is a vector, so conservation works component by component. If the net external force in the x direction is zero, x momentum is conserved, even if y momentum is not. In projectile motion without air resistance, horizontal momentum is conserved while vertical momentum changes due to gravity. What about friction and air resistance? They do not destroy momentum, they transfer it. If you track only a sliding box, friction is an external force and the box's momentum changes. If you expand the system to include the Earth, the total momentum of box plus Earth is conserved. There is an even cleaner way to see all of this. Total momentum equals total mass times the velocity of the center of mass. If no external force acts, the center of mass moves at constant velocity, no matter how violent the internal motion is. At the deepest level, momentum conservation comes from symmetry. If the laws of physics are the same everywhere in space, then momentum must be conserved. That connection survives far beyond Newton's laws. So the practical rule is this: define your system, identify external forces, and check which directions have zero net external force. Where that condition holds, momentum is conserved.